Okay, so all of you have completed your. Oh, I think I forgot to generate an assignment for this experiment number 5 and 6 last time, right? Have you all
Yes,
submitted your experiment 5 and 6?
ma'am, we don't.
Yeah. Okay, okay. Okay, then I'll generate it today. So you may submit it by today, 2 p.m. Okay, up till
Can you do it
experiment number 6.
evening, ma'am?
Okay, evening then by 5:30. Please submit your lab notebooks of this experiment number 6, up till experiment number 6 at least. Okay.
Yes, ma'am.
Okay. So yeah. So today I will be explaining experiment number 7. We have already done up till stimmy trigger, and today I will be explaining experiment number 7, that is the A-stable multivibrator. Right. So my screen is visible.
Yes, ma'am.
Okay. So what is a multivibrator? Okay, let's first find out when it was introduced and when it was by whom it was described for the first time. The Henry Abraham and Bloch described the first multivibrator circuit in 1920, and they called it a plate coupled multivibrator. And the picture is given on the right hand side. And initially it was made up of vacuum tubes, because you can see in 1920 the bipolar junction transistors were also not in existence, right? So that time people used to work on the vacuum tubes. Okay, so using those vacuum tubes, the first multivibrator was invented, and its harmonics were used to calibrate the wave meter. Okay, so there are three kind of multivibrators depending on the type of operation. So first is the astable multivibrator. It has no stable states. That means the output oscillates between two quasi-stable states. Okay, right? There is no stable state, so that is why it is known as astable multivibrator. Okay. Then comes the monostable multivibrator. That means there is one stable state, however, the other state is unstable, right? So the circuit automatically switches from the unstable state to the stable state. Okay, and to make the circuit go to the unstable state, you have to give some external trigger, right? When some external trigger is given, then only from the stable state the multivibrator will move to the unstable state. Okay, and unstable is already unstable, so it will not be in that unstable state for longer time. So it will automatically come to the stable state after some time. And on what thing it depends? This switching off between the unstable states, it depends on the charging and discharging of the capacitor which we will be using in the circuit. Okay, then comes the bistable multivibrator. It remains in either of the state indefinitely. If you have not applied any trigger, then the circuit will rest in the either of the stable states. Okay, so for moving between the two states, you have to give external trigger every time for both these states, right? So this is all about the multivibrators. Means there are three types of multivibrators: astable, that has no stable state; then monostable multivibrator, that has only one stable state; bistable multivibrator, that has two stable states. Okay, so you can imagine like a square wave. If you are giving a square input, then what will happen for a stable multivibrator? You need not to give any external trigger. Okay, no means no input is given, right? The output will automatically, once you have applied some means some input you have applied, some square wave input you have given once, then it will automatically vibrate between the two unstable states. Okay, so there will be the output kind, this square kind of wave at the output automatically. Okay, so in between you do not need to give any trigger, so that the operation of the means the output should vibrate between the two modes. You need not to give, it will automatically generate one square wave. Okay, then for monostable, there is one stable state. So if the circuit enters that stable state, then you have to provide some external trigger to move the output from the stable to the unstable state, right? So there are different kind of applications where we use all these three kind of multivibrators. So today we will be doing only the A-stable multivibrator. So this is a, you can say this is a black box. A-stable multivibrator is kind of a black box, and the input is none, but the output is kind of a square input, as you can see, right? And T1 is suppose 0, then the T2 will be 1. That means there will be, if there are two BJTs we are working on, then if one is on, then the other will be off. This kind of thing you will be seeing. Okay, and it generates square waveform without using any external trigger pulse, and is known as the astable multivibrator. It is also known as the free running multivibrator. Okay, so this is the circuit which you will be working on, right? You can see the C1 and C2, and the C1 is connected to the base of Q2 transistor, and C2 is connected to the base of Q1 transistor, right? So you can see a cross coupled feedback network, right? So once the suppose Q1 is on, right? So then what will happen? The C2 will get charged, right, up till VCC, okay, through R1. Are you getting? Through R1, this, wait a minute, I'll show you. Yeah, so like this. Suppose we have assumed this Q1 is in on state and Q2, this Q1 is on and this Q2 is in off state, right? So VCC will drop, there will be some drop across this RL2, right? So VC1 will be equals to 0. Here it will be 0, the voltage across this, right? VC1 is what? The collector voltage of this Q1, right? So this will be 0, and the point A, this point A is at the ground potential. That means the potential at this point is 0, right? So now this VC2, this VC2, that will get charged this through VCC, this capacitor will get charged up till VCC. Got it? Okay. And whatever voltage is there in C1, this C1 will get discharged, right? And the current will be flowing like this, okay, as shown in the figure. So what you will get at the collector of VC2, at this you will get some output like this, okay, and at the base of this VB2, it will be 0 because this is in off state, and at the base of VB1 there will be some input because it is because this C2 is getting charged. Okay, so this will increase very gradually like this. All right. And VCC is, what we have given, that will be equals to this VC1. Okay. Okay, this VC1 will be 0 at this point of time, because at since VC1 is 0, okay, so this will be grounded. This will act as grounded. So this VC1 is 0 here. Okay, got it. Now, what happens when this VC2, sorry, this C2 is charged up till VCC. Now, what will happen? Now, what will happen? Now, we consider that Q2 is on and the Q1 is off, right? So, what will happen? VCC drops across this uh, RL1, right? RL1, and hence this VC2 will be equals to now 0, right? So point B is now grounded, and this C2 will get discharged, and this C1 will get charged, and the current will start flowing in this direction, right? So C1 is getting charged and C2 is getting discharged. Okay, so this Q1 Q2 is off, sorry, on, and Q1 is off, and the waveform you will get it is like this base current of 1, this base current will go to 0 now, right? And this collector voltage at this terminal will now be what? This collector voltage will have some value, right? And the collector voltage of VC1, sorry, this collector voltage VC2, this will be 0, and this VC1 will be equals to VCC now through this. Okay, so now VB2, at the base of 2, there will be some increasing voltage because the C1 is getting discharged, right? So it is providing some voltage and it will increase gradually, okay, till it gets on, okay. And after it is on, it will become constant, okay, that will be equals to around 0.7 volts, right? Then what is about VC2? VC2 is 0, so it will drop to 0 like this. Okay, we are seeing only after this point. Okay, this point we are seeing, right? These are the two conditions which we will have when Q1, once the Q1 is on, and once when the Q2 is on. Okay, so what is the time constant? What will be the total time period when Q1 is off and when Q1 is on? So this is the total time period, and it will be equals to 0.69 times of R1 C1, because in this duration R1 and C2 are working, and in this duration C1 and R2 are on. Okay, so this will decide the total time period of the this whole cycle. Okay, so that will be equals to this plus this, because for the half cycle R1 C2 are working, and for the other half cycle C1 R2 are working. Okay, so this is T1 and this is T2, and just opposite you will get for the Q2 transistor. When this Q1 is off, this Q2 will be on, and when the Q1 is on, then Q2 will be off. Okay, so the frequency of oscillation, as you know, that is given by the inverse of the total time period, and the total time period is calculated by T1 plus T2, and that is equals to 0.69 times of R1 C2 plus R2 C1, because for half cycle R1 and C2 are working, and for the other half cycle C1 and R2 are working. All right. And suppose if we have R1 and R2 equals to, they have same value, and C1 and C2 also have the same value, then both these stages will be symmetric, and you will get a perfect this square at the output. Okay, so that will be, then in that case the time period will be 1.38 times of RC. Okay, and if we calculate the frequency for it, frequency of oscillation will be given by zero point 0.7 upon RC. Got it? So, what are the applications of this A-stable multivibrator? They are used for low clock frequency pulses. Okay, then they are used in the relaxation oscillators. Okay, and these relaxation oscillators are actually used in the vehicle indicator lights and the oscilloscopes and television receivers. Then they are also used for the timing signals, right? Okay, so this is about the A-stable multivibrator. So this same waveform is given in your manuals also. So try to achieve this kind of waveforms at the output, and you have to show the output at VC1 and VC2 both. All right. Also check for the base at the base terminals also. Okay. Then uh, okay, if you have any doubt, you may ask. Any doubt in this?
Ma'am, what conditions is there any condition, ma'am, regarding the other resistors and capacitor to get a proper waveform? Because in the last class when I tried it,
Yes,
I'm not
yes,
getting a
yes,
proper
yes,
waveform.
yes, of course, of course. Because if you will have a capacitance of very low value, so to have some very good amount of frequency, right? So you should have the resistance and capacitances of appropriate value, right? So as you can see, let me show you. Yeah. So, as you can see here, this frequency is what happened? Okay, this frequency is inversely proportional to time, right? So, if you are having this kind of output, okay, so if your capacitance value is very large, right? If the capacitance value is very large, then the frequency will be very low, right? If this RC is large, then frequency will be low, and this frequency will be high if you have this RC value low, right? So what will happen? You have to take means you need this frequency to be large. Then this capacitance and resistance value should be taken less. Or if you have a large capacitance, what will happen? Will it charge and discharge quickly or not? If the
Ma'am,
capacitance value is low,
it takes some time.
yeah, it will take some time, right? So that is why you have to take a capacitance value that gets charged and discharged very quickly, so that you can achieve this kind of waveform. Means this means this perpendicular kind of thing. That means it is getting charged very quickly. Otherwise, you will get this kind of waveform, right? This. So that means it is taking a lot of time to get charged and to get discharged, right? So you need not to get this kind of waveform. So you have to choose your capacitance as well as resistance value, so that the two things are there. Your frequency should be high, and the other thing is that your capacitor value should be like that. It does not get charged and discharged. It does not take much time to get charged and discharged. Okay, appropriate values you have to take. I think some values are given in the lab manual as well. So first try with those values. If you will not get any means the this kind of nature at the output, then you may try changing the capacitance and the resistance values. Okay.
Ma'am, one more doubt, ma'am.
Yes.
When R1 equal to R2, ma'am, then how which switch will get on first or get off first? Is it something like that? Because I'm having a doubt, ma'am. Like if R1 and R2 are same, then
No,
how
no,
will
if
that?
R1 and R2 are same, then also no issues because only one resistance and one capacitance will be working at a time. Are you
Yes.
getting? Because if you see this figure, right? So only one resistance and one capacitance are active at a time, right? When this point when this point is at zero terminal, then this R2 is already grounded. It will this R2 and this RL1, these both will act as grounded, right? So they will not work. So the current will be flowing like this only in this loop only. So at that time, this circuitry will not work. Only this capacitor will get discharged and sorry, yeah, so this capacitor will get discharged, okay, and this C2 is going to charge only. C1 and C2 will be working either charging or discharging, right? But R1 and R2 will work at a time only. Getting my point?
Yes, ma'am.
So if R1 and R2 are of same values, it will not impact the working of this circuit. Okay.
Yes, ma'am.
Any other doubt?
No, ma'am.
Okay. So I think you should start doing your experiment now. And if you have any doubt, you may ask in between. So our today's task is to do this experiment number 7 only, and who will already who have already done, because there are some people who I think have already done this experiment also. So they may proceed for the monostable multivibrator, that is the experiment number 8.
Ma'am, we are getting a straight line, ma'am, here.
No, 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 no. Straight line you should not get.
Ma'am, for all the four, I'm getting the straight line only, ma'am. I use the same diagram as the manual.
No, then there is some issue. Check your connections once again. Maybe some line is not connected properly.
Ma'am, we have to run it in DC mode only, no, ma'am?
Yes, yes, in DC only.
Ma'am, there is no problem, ma'am. Connections, I checked it again, ma'am.
Then what is the issue? Mm, okay. Okay, try using the R1 and R2. Take some lower values of R1 and R2.
No, ma'am, same thing we're getting.
No, there is no variation means there is some issue, right?
Yes, ma'am.
Yeah, straight line is means nothing you are getting. Values of R1 and R2 are not changed yet.
Yes, ma'am. What, ma'am?
Values of R1 and R2 have you changed?
Yes, ma'am, I have kept them as
Not,
five.
no, no, no. I'm not asking for RC1 and RC2. RC3 and 4. Do not change those values. I'm asking about this base resistances.
Ma'am, I'll change the base resistance. One second.
Yeah. Keep RC3 and RC4 same.
Yes, ma'am. I'll just revert it back. Ma'am, but it should be greater than RC1 and RC2, no, ma'am? Like RB1 and RB2.
No, where is it written?
Ma'am, I have done it from 10,000 to 5,000, ma'am. RB1 and RB2, ma'am, here.
Okay. Take it like 2 kilo ohms.
Yes, ma'am. Ma'am, again, we are getting the same thing.
Why is it happening? Actually, this can be corrected. Means if we are lowering the values of resistances, that can only correct the this triangular shape or that square shape what you are getting at the output. But you are getting a constant voltage, right?
Yes,
So
ma'am.
that is some other issue.
Ma'am, should I
Mm,
reduce it more, ma'am? I'll reduce it to 0.5 kilo ohms. Ma'am, again, same thing.
because you're not getting any variation, you're getting a DC kind of output.
Yes.
Why? So, is it that same connection that you showed last time,
Yes.
or you have
No,
made it
I
again?
made little bit different, ma'am. Last time, ma'am, I have connected little bit wrong, ma'am. I connected the collector terminal here, ma'am, at this point.
Hmm.
So, ma'am, I have changed my mistake, ma'am. Now I kept it here at this point.
Mm-hmm. Are you connecting the CRO appropriately?
Yes, ma'am. Like at the collector terminal, ma'am, I kept my positive output, ma'am, here plus at the collector
Hmm.
terminal of Q4 here, and I have grounded my negative terminal, ma'am.
Hmm.
Here also it's same, ma'am. The A positive side is connected to positive terminal, collector side of Q3, ma'am, and the negative terminal is grounded, ma'am.
Connection seems to be fine, but I don't know what is there. Okay, let's wait for some other student. If
Ma'am, but when I'm taking your AC value, ma'am, so I'm getting the variation, ma'am, but it's very low, ma'am. I'm getting it in femtovolts, ma'am, and the variation is also like varying in a random manner.
okay, show me the AC variation.
It's like this, ma'am.
Okay,
And ma'am, when I'm
it's too
comparing it,
much distorted. It's like too much of noise is present in the signal.
yes, ma'am. Ma'am, in the lab manual, they gave one more circuit, ma'am. I tried that one also.
Okay, yeah. So for this circuit, are you getting some results?
Yes, ma'am, little bit. It's better than before, ma'am. No, ma'am, it's same, ma'am.
Mm, okay. I think it should come, but I don't know what is the issue. Because if there is a circuit in front of your eyes, then I can sort out what is the issue. But since you are working on a software, so it is very difficult to find out the problem. That too on a remote machine. Okay. Okay, let's wait for some other student to finish first.
Yes, ma'am.
Let's see if others are getting or not. Okay.
Ma'am, similar graph, ma'am. Constant DC line.
Are you checking for the AC variations? Both are same. How is it possible? Values of uh, resistance and capacitance. Please try those values. For R1 and R2, take 80 kilo ohms, around 80 kilo ohms. Harsh, am I audible?
Yes, ma'am. Yes, ma'am.
And for capacitances, reduce the value of capacitance and take it as 100 nanofarads.
Okay, ma'am. 100 nanofarads.
Yeah.
And ma'am, RC1, RC2.
RC1, RC2 should be 1 kilo ohm only.
Okay, ma'am.
And also do one thing, uh, between this RC1 and capacitance C1,
Yes, ma'am.
uh, please just add one LED so
Yes, ma'am.
that we can see if the LED is glowing, that means the current will be flowing through it, right?
Ma'am,
And
it's
the same
C1
thing
and
you can
C1.
do, yeah, between C1 and RC1.
Yes, ma'am.
And again, similar kind of LED, you can two different LEDs. One should be blue and one should be red, just like that. So one more LED you may connect between RC2 and this C2. Means in series with RC1 and RC2, you can put two LEDs, right?
Yes, ma'am.
And change the values of capacitor as 100 nanofarad and the values of R1 and R2 as 80 kilo ohms.
Yes, ma'am.
Blinking, right? That means the current is flowing alternatively, right? Oscilloscope is not showing. Okay. Still not showing capacitance values. Have you reduced the capacitance values? Okay.
Ma'am, we are observing a square wave in the oscilloscope.
Observing?
Square wave.
Yeah, yeah, yeah. Square wave should be there only. Yeah. Show it to me. What output you are getting?
1 minute, ma'am. Ma'am, is my screen visible?
Yes, yes. Yes. You are getting correct output. This should be the output. So you have connected the these oscilloscopes at the collector of different transistors, right?
Yes, ma'am.
So you can see when one transistor is on, the other is off, and you are getting the pulse waveform. The output is correct. Also, your LEDs are blinking alternatively,
Yes, ma'am.
right?
Definitely.
That means when this uh, when the current is flowing through one side, then that side LED is glowing, and when the current is glowing through the other side, then that side LED is glowing, right?
Yes, ma'am.
So that's correct. That's all what you have to do. Also, you have to calculate the frequency in here. Calculate the time period. T equals to R1 C1 0.69 times of R1 C1 R1 C2 plus R2 C1, and then calculate the frequency theoretically. And then from here, what is the frequency?
1 minute, ma'am. So it's 6.3 milliseconds, and here it is 6.45 milliseconds. Ma'am, I'll just calculate it on that.
Hmm. So students, can you see the output? This kind of output you should get. Harsh,
Yes, ma'am.
are you getting
No, ma'am,
something?
I'm trying it.
Okay.
Ma'am, it's 150 hertz.
150 hertz. And calculate it theoretically.
Ma'am, it's 90 hertz theoretically. No. Yes, ma'am, it's 90 hertz theoretically.
90 hertz. And
This is
practically you are getting
150. I guess I have measured it wrong. I'll just check it again.
hmm.
Ma'am, yes, ma'am, they are the same. Uh,
Okay.
Here it's 90 hertz, like 6.3, 639 milliseconds and 650
Hmm.
milliseconds. So the
So they
frequency,
are matching, right? They are in proximity with each other, right?
yes, ma'am.
Okay. Please show me your circuit once more.
One circuit.
Okay. Fine, that is okay.
Okay.
Okay. Please try connecting the oscilloscope at the base terminal also, and see if you are getting the same kind of that waveform which is given in this manual.
Okay, ma'am.
Okay. So students, have you seen the output of Shashank? You should get that kind of output.
Ma'am, I think now this is the correct output because I have attached a resistor over here previously.
Over where?
I just removed it right now. This ground I have connected a resistor temporarily.
Mm-hmm.
So this one is the correct output.
Okay, this is also fine. Check the frequency.
Yes, ma'am, I got the output, ma'am.
Harsh, you got the output?
Ma'am,
Yes.
it's the same frequency, ma'am.
Okay, fine, Shashank. Shashank, you may please stop sharing.
Yes, ma'am.
What is your roll number?
I'm 212.
Okay, wait.
One. Yes, ma'am.
Ma'am, can I share, ma'am?
Just a minute. Okay, yeah, please.
Ma'am, is my screen visible, ma'am?
Yes, yes.
Ma'am, the LEDs are blinking, ma'am. I kept them.
Mm-hmm. Yes, okay.
This is the output waveform I'm getting, ma'am. At one
Okay.
of the collector
One
terminals.
collector. Hmm.
Ma'am, this is the output at another collector, ma'am. Second collector terminal.
Okay.
And ma'am, this is the output at base terminal, ma'am.
Yeah, that's correct.
Yes, ma'am. And at another base terminal, I got
Hmm.
this value, ma'am.
Yes, 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 fine. So please check the frequency also
Yes, ma'am. I'll
and
calculate it now, ma'am.
compare the theoretical and practical values of frequencies.
Yes, ma'am.
Okay, fine, Harsh.
Thank you, ma'am.